In Chapter 13, we were studying vector functions. Now for those, our input was one-dimensional. Our input was just a number. And then the output was multidimensional. We'd get a vector in either 2 space or 3 space. And sometimes it was helpful to think of that as an arrow, but graphically we were generally associating that with a point so that we were getting curves in 2 space or 3 space. In Chapter 14, we're going to look at a different sort of function. We're going to be looking at functions where the domain is multidimensional, although the codomain is still going to be just the real numbers. So now we'll be inputting a point in n space, in either 2 space or 3 space, and associating that with a number. So if the domain is a subset of 2 space or 3 space, our functions are going to map that domain to the real numbers. A point, what's nice about just using p for point is that could be a point in 2 space or in 3 space. If I'm in 2 space, I'll very often just write xy. If I'm in 3 space, I'll generally write xyz. But if I want to be able to talk about functions of more than one variable without having to write things twice, once for 2 space and once for 3 space, I can just say my input is a point, and then my output would be a number, f evaluated at that point. Now, when we're graphing these, when we were graphing our vector functions in Chapter 13, we graphed the output only. There was no t-axis, even though t was our input. When we're graphing these things, we're going to be graphing essentially the input, comma, the output. So that's going to be a bunch of points in our n plus 1. Okay? We're going to have n variables for our input and then 1 more for the output. So if my domain is a subset of 2 space, the graph is going to be a bunch of points in 3 space. Now I can think of that as my domain would be all or part of the xy plane. What my function is doing is that's attaching a z value to all of the points in the domain. So I take a point on the xy plane. If z is 3, I move to the point in 3 space that's 3 units above that. So we're attaching a height, which could of course be a negative height. We could be below the xy plane. We're attaching a height to points that are in our plane. Okay. So the graph, if the domain is part of 2 space, we're going to be getting some sort of a surface in 3 space. Or if my domain was a subset of 3 space, now my graph is going to be in 4 space. Now, we're going to have a hard time visualizing that. Unless you're very strange or magical or a different species, you're going to have a hard time picturing that because we live in a 3-dimensional world. Okay? So we will be able to work graphically with functions of 2 variables and their graphs. It's going to be harder to visualize what's happening in 4-dimensional space because we don't have a physical model of that. But we'll be able to work algebraically with that and sort of use some geometric metaphors to understand what's going on. So we would call the graph a hypersurface in 4 space. And rather than trying to visualize what that looks like, we'll just accept that that's a collection of points in 4 space, just like a surface is a collection of points in 3 space. Okay, so let's take a look at some examples. And I'm going to start with functions of 2 variables because those we can understand a little bit better because we've got the graphical approach. So let's suppose I had f going from 2 space. That's going to be my domain now, so it's defined everywhere. I'm going to send xy to x squared plus y squared. So I could write this as f of xy is equal to x squared plus y squared. But f of xy is just a fancy name for z. So this is z equals x squared plus y squared. We've seen that before. That's actually just a paraboloid. That's one of very few quadric surfaces we're going to see that are actually graphs of functions. Because remember, the rule for a function is that each input has to have a unique output associated with it. So for every point on the xy plane, if that's my domain, or for every point that's in the domain, if it's some subset of that, there's going to be a unique z value. So 1 point above or 1 point below, or if the z value is 0, 1 point on the xy plane there. But I can't have multiple z values associated with a point, or this wouldn't be a function. Each input must have a unique output. That essentially means that the vertical line test that we have for checking to see whether we have a function when we're just graphing things on the xy plane, that vertical line test translates into 3 space. So here, any vertical line would intersect the paraboloid at most once. However, if I had something like a hyperboloid in one sheet, a vertical line is going to intersect that more than once, because I'd have a point here and here that would have the same x and y values, but different z values. Orienting it so that it was, lying on its side, something like this, wouldn't change that, because I would have a point up here and a point down here, different z values, but the same points x, y. So most of the quadric surfaces that we've studied fail the vertical line test and are not, in fact, graphs of functions. Let's take a look at a few more things, though, that are functions. If I have f of xy is equal to ax plus by plus c, where a, b, and c are just constants, okay, we should be able to recognize this. That's just a plane. Because remember, f of xy is just a fancy way of writing the output, and if the endpoint is a point xy, the output's going to be my z value. Okay. All right, I do need to be a little bit careful. The normal to this plane is not ABC. So we've often used ABC for the normal, where we had AX's plus BY's plus CZ's. Here I don't have CZ's. If I were to put this in standard form, I would subtract that Z over. So I'd have 0 equals AX plus BY minus Z plus C. So the normal is actually A, B, negative 1. Okay. But you'll notice that's algebraically, it looks like just a linear function. The types of terms we have are sum of each input variable and a constant. That we call a linear function, and that gives us a plane. I could have something like this. G of xy is equal to the square root of x squared plus y squared minus 1. Now, at first glance, we may not recognize what that is, but I'm going to just say that this is z, and I'm going to do a little bit of algebra to make this look a little bit more familiar. I can say z squared would be x squared plus y squared minus 1, squaring both sides. Now, when I do that, I need to be very careful, because this put an inherent restriction on z that's not obvious after I square both sides. Since z was the principal square root of something, z was non-negative. So I just need to record that z is not negative. Now I look at this. This looks to me like an equation for a quadric surface. Now I mentioned most quadric surfaces are going to fail the vertical line test, so that their graphs won't be graphs of functions. However, this is just part of the quadric surface. This is the top half. Okay. So let's get this in standard form. I think I'm going to add over the 1 and subtract over the z. So we'll have 1 equals x squared plus y squared minus z squared. And I can recognize that's now a hyperboloid in one sheet, because there's one negative sign. Okay. The oddball sign is the z's, so this opens on the z-axis, and because z is bigger than or equal to 0, we're talking about the top half of this. So we're talking about the top part of a hyperboloid in one sheet. If I were to draw in the bottom half, then we'd fail the vertical line test. Notice, if this was negative the square root, that would give me the bottom half of the hyperboloid in one sheet. So most of the quadric surfaces that we have are going to be like this, where if you solved for z, you'd have to take plus or minus the square root. The positive square root will give you the top half of the quadric surface, that's one function. The negative square root would give you the bottom half of the surface, and that's the other function. So, I want you folks to try this one. Z is the square root of x squared plus y squared. Before the next video, see if you can figure out what this looks like and graph it. And you're going to do something similar to what we just did. It's going to be a lot easier if you square both sides, but then record that z, because it's the square root, must be non-negative. So give that a shot. We'll take a look at that together in the next video.